SwayamPrabha. Digital India. Educated India.
Welcome back. So in the last lecture we were discussing Exergy. We will continue our discussion, particularly fixed mass or closed system. Okay. So consider system where the state changes from, let's say, 1 to 2. So this is your system state. Okay. So you can consider this system having interaction. So this is system, let's say at T. Okay, and having a heat and work interaction, and heat flows from surrounding to the system, and surrounding temperature is T0, let's say, and T0 is greater than T. T is your system temperature. Now considering this is a finite temperature, hence it's irreversible. So to make heat transfer, okay, reversible, what we are going to consider Carnot engine, okay, which operates between T0 and T, and it receives some Q0 from surrounding and produce some work W reversible, let's say heat engine, okay, and it rejects Q at T. So in other words, I can represent this system in the following way. Okay, so it considers T0, Q0 and W reversible, Q, and this is your system. Okay. So the other thing which we will be assuming is that the system in this process changes its volume. Okay. So let us now assume that volume of the system increases from V1 to V2. Okay. So in other words, what we are saying is that during this process, system does work against the surrounding. Okay. So this is the work would be corresponding to P0 V2 minus V1. Okay. So now what we can do is we can find out what is the maximum work corresponding to this system, or maximum work which can be maximum work delivered by the system. So this is going to be your reversible work by the heat engine plus W by the system minus the work against the surrounding. Okay, so this is going to be your W max. Okay, we can find out the W reversible heat engine value by simply doing energy balance. So W reversible work done by the Carnot engine would be W reversible heat engine is Q0 minus Q. Okay, and we know that for a reversible heat engine, your Q0 by T0 is nothing but Q by T. Okay, so this is by for the Carnot engine which we have earlier developed, and this is nothing but your S2 minus S1. Okay, so this is based on the fact that your ds for the reversible case is delta Q by T, and then this integral would be this for the case of reversible, and thus your change in entropy would be simply your Q0 by T0 or Q by T. Now we can simplify the expression of work maximum. This can be written in the following way: your W reversible heat engine Okay. So, let me also make a point here that your W, we can also do a energy balance, apply the first law of thermodynamics for the system, where we can write Q minus W as simply delta ES. This is for the case of your closed system. So, this is heat supplied and this is the work done by the system, okay. And this we can write as E2 minus E1. So, this also means that W is Q plus E1 minus E2, okay. We can express this here and write your W max as simply the following way: Q0 minus Q plus Q plus E1 minus E2 minus P0 V2 minus V1, okay. Now, this expression which we have written for reversible heat engine can now be made use. First we can cancel these Q's, and Q0 can be written as simply T0 S2 minus S1 plus E1 minus E2 minus P0 V2 minus V1, okay. And considering the kinetic energy and potential energy changes as 0, we can write this just simply U1 minus U2. So, I can rewrite this expression in this form: U1 minus my U2 plus P0 V1 minus V2 minus T0 S1 minus S2. So, note that what I have done is I have swapped this particular variable and the negative sign is now converted to positive, okay. So, we have rewritten in this way, okay. Now, this particular expression is what we are going to write as useful maximum, okay. This is nothing but your Exergy. In this particular case, we have taken your T0 greater than T, but this derivation is also true if you had taken your T0 less than T, okay. So, in other words, your Exergy is for the closed system is greater than or equal to 0, okay. So, now you can consider your T0 as a limiting case as an environment, and if that is the case, then U2 would become your corresponding surroundings. So, as I was saying that this if you consider your 2 to be your surrounding, then we can write the useful maximum for given state of a system in the following form, okay. So, we can write simply in this following way. So, we can write your W useful or total useful for a given system as simply U minus U0 plus P0 V minus V0 minus T0 S minus S0, okay, where 0 here is represent dead state, okay. So, what you are doing is you are changing your system condition for a given specified system state to corresponding to the taking the system state to the dead state, and during this process whatever the work which is being generated is the maximum possible work, okay, for in the considering this a reversible way you are able to do this operation. And this is the expression for the total useful work, where 0 subscript represent the dead state. In general, closed system may possess a kinetic energy or potential energy, so you may have to write this expression or for the general expression of the Exergy, okay. So, this instead of saying W total useful, we are making use of this particular symbol X here for the Exergy of the system. One can rewrite this in terms of unit mass, where U becomes small u and the rest of the terms the mass cancels out. So, everything is in the specific unit. The change in an Exergy of a closed system is simply the change in x, that is x2 minus x1, and that can be written in terms of phi m times phi 2 minus phi 1. So, naturally this can be written as E2 minus E1. Now, since the kinetic energy is included, so we simply say E2 minus E1 plus P2 plus this term, the pressure multiplied by the volume term, minus this term. Okay. Or you can simplify this in terms of U, and of course, you have to consider the kinetic energy difference and the potential energy difference if you want to expand your E. Okay. And thus your Exergy change for a closed system can be written as simply the change in the internal energy, P0 multiplied by the change in the volume, minus T0 multiplied by the change in the entropy, and the kinetic energy difference and the potential energy difference. Now, this becomes Exergy change of a closed system. You can rewrite this expression in terms of unit mass basis as described in this form. Okay. In case of system is not uniform, one can also calculate Exergy, as Exergy is a state property. Okay. The reason for that is very clear, that other property which is associated with are state property, and hence you can simply integrate this over the volume. Okay. And that is what we here as we shown for other state property cases. Exergy for a nozzle, compressor, turbine, pumps, heat exchanger during in a given environment during steady state should be 0. Okay, because for a steady state there is no change in the energy conditions, and that means there is no change in the property of the system for the steady state, and hence Exergy for nozzles, compressor, turbine, pumps, heat exchanger has to be 0. Okay. As I was saying that for the case of a closed system, the Exergy can be positive as 0 but cannot be negative. And the expression is true for cold system or hot system, which essentially means that the T of the system can be greater than the surrounding or the less than the surrounding. Okay, so because you can come up with any specific heat engine with and consider the system as your sink or the source. Okay, so the expressions are true for irrespective of the different signs of the temperature with respect to surrounding. So, the expression which we have developed was for the case of a closed system. We can extend this expression for Exergy for the case of flow systems or flow streams. So, let us consider this now. So, the flow work here is nothing but is equivalent to boundary work by a fluid on a fluid downstream. So, flowing fluid has to do work in order to displace the fluid here, and thus your PV is the flow work is nothing but your P0 work plus the W shaft. Okay. And thus you can write that Exergy associated with the flow energy is nothing but X flow PV minus P0V, and this is the amount which if you consider imaginary piston, this is the work which it does on the surrounding by displacing the air, and thus you have to subtract it in order to get the Exergy associated with the flow energy, or in other word P minus P0 V is the Exergy associated with the flow energy. So, thus you can write your Exergy of flow stream simply as X flowing fluid is nothing but X non-flowing fluid plus X flow. Okay. Or that means you can write this as U minus U0 plus P V minus V0 minus T S minus S0. So, we can have the kinetic energy and potential energy terms plus P minus P0 V. Okay. You can rearrange this in terms of U plus P minus U0 plus P 0 V0 minus T0 S minus S0, and these terms can be written as well, and this can be written as now H in terms of enthalpy H minus H0 minus T0 S minus S0 plus your kinetic energy plus potential energy. Okay. So, thus your flow Exergy, now note that I am writing flow Exergy not energy here, is defined as psi, and this is the term which we defined this. So, this is nothing but your psi. Okay. This is your flow energy. Okay. So, we can also find out the Exergy change, and that will be your delta psi will be your psi 2 minus psi 1. So, Exergy change of a closed system of a fluid represent the maximum amount of useful work that can be done or minimum amount of useful work that is needed as the system changes from state 1 to state 2. Okay. So, thus Exergy represent the reversible work. Exergy of a flow system, however, can be negative because it depends on your pressure. So, let us look at your term here. We mentioned this in terms of your psi was your u minus u0 plus p0 v minus v0, okay, minus t0 s minus s0 plus v square by 2. Then you have this p minus p0. Okay. So, if this turns out to be quite high, or in other words, if p is quite low than p0, then this would be negative term, and hence your psi for the flow system can be, or psi can be negative. There is a possibility of being negative as well. Okay. So, let me try to do an exercise here. So, this is your 200 meter cube rigid tank, contains compressed air at 1 megapascal and 300 Kelvin, and what we have to do is to find out the work which can be obtained from this air if the environmental conditions are 100 kilopascal and 300 Kelvin. So, we need to find out the exergy, okay, the maximum work which we can extract. So, the first thing we need to do is find out the mass. Okay. So, the mass can be calculated from here. Then we need to find out your, it is a closed system. So, we are going to use x1 m phi 1, okay. And what is your phi 1? So, phi 1 is your u minus u0 plus p0 v minus v0 minus t0 s minus s0. We will consider kinetic energy and potential energy to negligible. Okay. Now, this term, since it is an ideal gas, that is what we are going to assume for the air. This can be written as R T0 P0 P minus 1. Okay. What about this? Now, we will be using the delta S for the ideal gas. So, this is going to be Cp ln T1 by T0, okay, minus R ln P1 by P0. Okay. Now, note that the temperature is not changing here, that means state 1 to state 2 your T is constant, only the pressure is changing, correct. So, if that is the case, this is 0 because u is same as u0 for the ideal gas, and this would be also 0, okay, because T1 is same as T0. Thus, this expression can be written as minus T0 minus of R ln P1 P0. Okay. So, one can calculate this, and this would be, so x1 would be your maximum useful work which can be obtained from this compressed air stored in the tank in the specified environment. Okay. So, that was the example illustrating the calculation of exergy of a closed system, and this would be the end of this lecture. In the next lecture, we will continue this discussion on exergy. Okay. So, I will see you in the next lecture.